All right, before we get to our second example, let's look at a theorem and then a table of some antiderivatives. First, if big F is an antiderivative of little f, then the most general antiderivative is big F of x plus c. I probably should say capital F of x, but big seems like more fun. All that statement is saying is that adding a constant to an antiderivative does not change the fact that it's an antiderivative, because when you differentiate, that constant would go away. And again, refer to the previous example to see that in action. All right, let's look at a table of antiderivatives. This is not a holistic table. By the way, your textbook on page 318 has a nice list, which is very much the same as these. Okay, these first two statements are just similar statements to what we have with derivatives. The first is, when you have a constant inside of or affecting a function, being multiplied into a function, it really has no effect on the antiderivative. So the statement here is the antiderivative of c times f of x is just c times big F of x. Again, what that just generally means is that constant in terms don't do much. They just chill out as you're finding an antiderivative. The second statement, and this could be the same with subtraction, is that if you have different terms in your function, you can anti-differentiate both of those, and that just looks like this. So you anti-differentiate the first term, and then you anti-differentiate the second term. Okay, so those are more tools of the trade. Let's get into the nitty-gritty. First, we have x to the n. Now what I call this is the anti-power rule. This is going backwards the power rule, and it looks like this. We're going to take our exponent and we're going to add 1 to our exponent, and then we're going to divide by that value n plus 1. In the next example, we'll see that in action. We have here x to the negative 1. Now, a very important caveat to that above statement that I should have said is that in this case, this is true for any n except n cannot be negative 1. Because of the following example. N to the negative 1 is 1 over x. The derivative of that for 1, if you try to put it in the anti-power rule, wouldn't give you out a value, and it would be a constant actually. Instead, we know that the antiderivative of 1 over x is the ln of x. And then the antiderivative of e to the x, well, this is the fun, easy one, is just e to the x, so it doesn't change in differentiation. The antiderivative of sine of x would almost be cosine, but because differentiating cosine produces a negative, the antiderivative of sine would actually be negative cosine of x. The antiderivative of cosine is sine of x. And then we get into some fun stuff, and there's many more of these examples. The antiderivative of 1 over the square root of 1 minus x squared is sine inverse of x. Now those are all, they are an antiderivative. What I just want to show here is you can add a constant onto any of these if I wanted to make these the most general form of the antiderivative. And that's an important topic that we'll cover in example 3. All right, but first let's look at this second example. In this case, we're asked to find the most general antiderivative of these three functions. F of x is 6x squared plus 10x minus 7. All right, so in this case, two things are at play. First, we can apply this strategy. Again, what that means is we can attack each term individually, which makes things very nice and a lot easier. And then this anti-power rule. And again, what the anti-power rule says is add 1 to the exponent and then divide by that new exponent. So let's look at this. So for f of x, I'm going to find big F of x. So first, this first term was x squared. Now it's going to be an x cubed term. And then I divide that by 3. And I'll just actually, in action, divide the 6 by 3 to get a 2. And again, you can look at that. So I made that 2 a 3, and then divided the 6 by 3 to get 2. And if you differentiate that, you can see that it becomes that 6x squared. And then the next step is to make that x to the 1 power an x squared, and then divide that 10 by 2 to get a 5. And then that constant term, which I don't have an example up there, but it's very easy to find the antiderivative of constant terms because you just got to throw your independent variable on there, in this case, x. Okay, let's move along to g of x. In this case, g of x, big G of x, I would differentiate each of these terms separately. E to the x, the antiderivative is nice and easy. It's just e to the x. And then the antiderivative of sine of x, as we talked about earlier, was a negative cosine of x. So I'll just write minus cosine of x. Okay, before I move on to the third example, or third part of this example, which is fairly difficult, but maybe you can see what it's going to be out the gates, I just got to make sure I'm asked for the most general form, so I need to add this constant on to each of these right here. Again, whatever that constant is when I differentiate would give me the original function. All right, let's talk about the h of x. This one is very strange and difficult. In general, this might look like an anti-quotient rule or something like that. What I'm first going to do is to rewrite this with the constant on top of 2 out front. This makes this a little bit easier to see. And what I can do with this is I can basically ignore the 2 out front. Again, that is from the property 1 up here in the table that says, hey, basically ignore constants in front of functions when you're differentiating them. Now, this isn't in my table, but you might be able to think, what is the antiderivative of 1 over 1 plus x squared? And what you need to think again is, what function when I differentiated gave me 1 over 1 plus x squared? And if you're thinking tangent inverse, you are a genius. In this case right here, I have 2 times the tangent inverse of x. And then, for my general form, I need to add that c value on there. So with those 3 examples, you're getting an idea of how this works. Again, you can ignore constants, just work with the variable part. Things like e to the x, again, are easy. They're going to suck in the future because we're going to throw stuff into that exponent, which makes things a little trickier. That's in Calc 2. But the anti-power rule is pretty straightforward. Going backwards with trig functions isn't that crazy once you know your properties and your derivatives of trig functions. And then you got to get into tricky things like part 3 of this example, to where you have to identify kind of these more obtuse or not so well known derivatives to find the antiderivative.